Hello there. We are talking about section 2.6, implicit differentiation and related rates. Second video is going to talk about related rates, examine applied problems involving related rates of change. So let's see if we can get there. Okay, so there's not really any new definitions to associate with this. I think the biggest caution that I can put out there about it is that this is more chain rule. So if you loved chain rule before, then you're going to love it some more, and if you hated it, then well, maybe we'll get better at it. So our situation is a sodium chloride crystal which is growing in the shape of a cube, and the claim is that it's increasing, the side lengths are increasing at a rate of about 0.3 millimeters every hour. So then our task is to figure out at what rate does the volume of this crystal grow with respect to time when the cube is 3 millimeters on a side. So this is one of those situations where you could read the problem and get no information out of it because it just sort of slips through your brain. But if we look at this kind of carefully, then we can break down all the pieces that we really want. So the portion that I'd like to focus on in particular is the actual request here, the piece that tells us the thing we're trying to figure out. So at least we have a goal in mind. Okay, so let's identify some variables that we want, variables that we know. At what rate, so there's some things that are called out here. At what rate really suggests that what we're looking at is the derivative of something. That's an instantaneous rate of change. Can't really get around that. Volume seems like a variable we should label, and V seems like an obvious choice, but you could pick anything, X, whatever. And how does this grow with respect to time? So this is maybe a new phrase that we're mostly seeing since we hit chain rule because it helps us identify what is the input variable of interest. So with respect to time means that yes, we're taking a derivative, but t is the variable of interest for input. And then finally, we want this derivative when the cube is 3 millimeters on a side. We haven't yet picked a variable for side length. Maybe s is the most obvious choice for that. So this is saying that we want the derivative of volume with respect to time when s is 3. Well, now we've at least identified our goal. Let's see if we can dig through the other pieces of information and find the things that help us get this goal. So one thing we might have to dig through is our geometry understanding and recognizing that the volume of a cube looks like the side length to the third power. And once we have this relationship, we're kind of off. Once we have an equation that relates the variables that we know with the variables we want to know, then life is pretty good. So we'd like to differentiate this with respect to time. And that's because ultimately our derivative wants to know what is the volume, the rate of change in volume as time goes on. So the nuance, dv dt and ds dt are going to be terms that crop up here because both volume and side length depend on time going by. So I am tempted to write simply 3s squared for the final result on this right side. Unfortunately, that's the beginning, but since the ultimate variable of interest is time, we have to tack on something due to chain rule. So just like with implicit differentiation, I'm supposed to think s actually is buried in there something to do with time. So when I take the derivative of s cubed, I'm really thinking the derivative of a bunch of stuff with t in it, all to the third power. Okay, so here is our equation all splayed out there. And the one extra piece of information we were given explicitly was that s was equal to 3, which is good, but we need a little bit more in order to get a final answer for dv dt. So if we look at this equation we're after, dv dt, this is the big question mark, so it makes sense that we don't know what this is yet. S is 3. It would be really great if we had yet this final answer. So the piece that we haven't made use of yet is that they told us side length is growing at a rate of 0.3 millimeters per hour. And in the beauty that math is capable of presenting to us, all this English turns into this one concise expression. ds dt, the rate of change in side length as time goes on, is 0.3. So now we can replace ds dt with that value, 0.3. Maybe a little color coding is in order here. So ds dt, this rate of change, we can just write 0.3 instead. And you might notice this whole right side has no variables on it anymore. So we can tidy all of that up to a nice round 8.1. And as always, trying to think about units. But we were given the side length was 3 millimeters. So our volume is going to be millimeters cubed, and then time would be in units of hours. So our rate of change is going to be comprised of those two things, cubic millimeters or millimeters cubed per hour. That is one of the advantages of this way of writing the derivative. It reminds me that volume is on top and time is on bottom. So its units must look like units on top divided by units on bottom. Let's try a businessy application. And truth be told, this is the kind of example of the harder type of thing that showed up in 2.4. So you probably won't think less of me for doing an additional example of something that could be like 2.4. But again, the truth is that the boundary between related rates from this section and just plain old chain rule problem from 2.4 is a pretty thin one. So we could see this type of question appearing in either section. Okay, so we've got demand. It does look like it decreases as the price gets bigger, so that's reasonable. It's got a weird square rooty thing in there we'll have to deal with, but that's all right. Then we also are told that the price itself decreases over time. So this is a common scenario. This relates how many units are sold with the price per item. But as the product itself gets older, we probably discount the price more and more. We don't see $100 camcorders that are these giant things that you fit over your shoulder anymore like we did in the late 80s. So price decreases over time, and the thing we're supposed to figure out is at what rate is revenue changing with respect to time 6 months after the item's release. So these are the key phrases to look out for. At what rate is revenue changing? With respect to time tells me the input, and then 6 months after release is going to give me a particular time that we're after. Okay, so dRdt, that's the rate of change in revenue. 6 months after release implies that t is 0.5. We have to be a little bit careful about units. T is measured in years, so 6 months would be half of a year. We don't actually have a formula for revenue yet, but we're getting pretty good at this. We know demand, so revenue would be price per item times the demand on that item, quantity demanded. So x times this 4 minus square rooty thing, and expand it out, just multiplying x to both terms gives me a revenue equation. It's a good place to start, but we don't actually have a rate of change in revenue just yet. We could do that though. One thing to note is that our equation has x's in it. It doesn't even seem to have t's. But remember that x depends, then that's the unit price. X does depend on time. So dRdt is going to look funny because initially it doesn't seem like we have anything other than x's. I can find the rate of change in revenue as the price changes. But there's going to be some chain rule piece that comes along. And remember, this is our alternative formulation for the chain rule. This usually saves us trouble when the expression that we're working with, revenue and maybe one for time, or excuse me, for price, when both of those things are kind of complicated, this usually saves us a little energy. Okay, so dr dx, just let's piece together our components here. Here's dr dx. It wants the derivative of that revenue equation we just came up with. And remember, chain rule is very forgiving in the short run. It allows us to treat this just like x's, even though the real rate of change is with respect to time. But before we're done, chain rule also makes us tack on the derivative of x with respect to time. But it's kind of convenient. They gave us an equation for x in terms of t, so we'll just have to multiply this whole revenue computation by the derivative of x. Okay, so here's what that actually looks like all played out. So the derivative of 4x would just be 4. And then this I'm saving for an additional step because it looks a little bit more exciting. The thing I'm supposed to pay attention to is that I've got x's in each of these two factors. They're getting multiplied together, so we're going to need product rule. And then we already tackled the derivative of the x stuff over here. So derivative of 6 minus t squared would just be negative 2t. So this piece is going to hang out for a little while, maybe just have a sandwich or something while we figure out what goes on with our product rule in this first set of brackets. So we're going to have some product rule at first, and actually buried within that there's going to be some chain rule too. So here we are. We've got all this first stuff, and let me see if I can do some more creative underlining here. Here's all the product rule excitement that's left in front of us. And here it is all played out. There's a monster, huh? So let's track this down. So product rule says, let's leave the first thing alone. So we'll leave x alone, and then we'll take the derivative of this other thing. So the derivative of this big square root deal is going to be 1/2. And then our exponent goes down by 1, so we're down to -1/2. But this we kind of cheated here. We pretended like this stuff inside here was just x. So chain rule makes us tack on the derivative of that inside piece. The derivative of that inside piece is 2. So there's all the chain rule from derivative of square root of interesting things. And then we're back to derivative of x again. Derivative of x is 1, sort of anticlimactic, and then we have just the square root thing one more time. So no more derivatives from that square root. We already took care of that hard part. Oh, there's a lot of color there. Very festive. Okay, so with a little simplification, we've got 2 times 1/2, which is going to mean those pieces are out of the mix. I just couldn't resist. You got to throw some more color on there. So all we have left is x. We have the 2x plus 1 to the -1/2, and we've got the square root piece. Since 1 times that isn't really changing it at all. And like I said, -2t is hopefully finishing up its sandwich here soon because it's just been hanging out while we take care of this other hard stuff. Okay, so it seems like we're ready to plug in numbers, but there is a catch. Our expression has, and I'll go back to it for a moment, has both t's and x's in it. So plugging in 0.5 for t is not an issue. Plugging in, well, I guess what for x? Well, that's fine, actually. We have a relationship that tells us what do we do when we've got t's. X knows what to do. If we have t equals 0.5, we can just dump that in for t and figure out that after half a year, the price per item is 5.75. I think it was in thousands of dollars, though, so this is probably some kind of spendy, something spendy we're going after here. But at any rate, x is 5.75. So then we have this monstrosity. We've got the RDT, which you might just be getting used to, and then this big subscript basically is just like a big at symbol, or this big vertical bar. I'm supposed to evaluate this derivative at all of these things. Well, so t equals 0.5, so there's t equals 0.5. We'll do like 73 colors on this picture. So 0.5, there's t, and then everywhere we've got x's as well, we can plug in 5.75, that was the thing we just computed. X appeared in a handful of places here, so it needed to get substituted in. But when all's said and done, we've got a value of about 1.162. And then as usual, one of the more challenging things is just getting some units on this. But we'll remind ourselves, we go back to revenue, we go back to time. Those tell us the units on this, because it's going to be revenue units per time unit. So at the 6-month mark, that's reminding us that t equals 0.5 was our input. Revenue is increasing because our derivative is positive at a rate of about, and here we have a little bit of work to do, $1.162 million is the claim. And that's because our demand, D, was in terms of thousands of items. And our X was in terms of thousands of dollars per item. That 5.75, remember, was actually pretty spendy. So when we multiply those two things together, thousands of thousands is actually millions. And then the per year is going back to our units on time, the denominator. So this really was revenue units per time units. And there's our derivative. That's it for our introduction to section 2.6. We'll do some additional examples in class, and we'll come back with a new chapter before too long. I know you're super excited about that.